Alright, so let's do this problem with Lebesgue's dominated convergence theorem. So we want to compute this. Notice first of all that this will be our sequence. So again, Lebesgue's dominated convergence theorem tells us that if we have a sequence of measurable functions f of x converging to f as n goes to infinity, and also we have a dominating function g of x, which is integrable, Lebesgue measurable, or Lebesgue integrable, then we can kind of pull this limit inside. So then limit as n goes to infinity of n of dm is equal to limit inside the integral, which is equal to f. Notice, I just want to make a note that we cannot apply the uniform convergence theorem because this function is not uniformly convergent. Moreover, okay, by the way, okay, let's follow these steps. So 4Ds, first define the sequence. Clearly, our f sub n is equal to n square root x over 1 plus n squared x squared. 2, there's no uniform limit. For example, if we pick an x that depends on n, so like x equals 1 over n, we have our f sub n is equal to n square root 1 over n over 1 plus n squared times 1 over n squared. This goes to 1, so we have this is equal to, and this is equal to n times 1 over square root n over 1 plus 1 square root n, so that's equal to square root n over 2. And then as we take the limit as n goes to infinity of this at a specific x that depends on n, we'll get this going to infinity. So we can only say that we have pointwise convergence, which means that if we fix an x, then eventually as n gets large, we will have our function go to 0. So basically now we can show this pointwise limit. So for the pointwise limit, not the uniform limit, right? Limit as n goes to infinity of n squared root x over 1 plus n squared x squared. Let's split it into 0, 1 and 0. So notice that, notice that for anything from 0 to 1, our bottom will blow up and then our numerator will get bigger, but not as big as the bottom. So it's equal to 0, and then at 0, the top just becomes 0. So our pointwise limit is just 0. Okay, so now we can find our dominating function. So our dominating function we can find with this simple inequality. So remember that 1 minus k squared is greater than or equal to, it's less than or equal to 2k. And we can see this because 0 is less than or equal to k squared. Plus, whoops. Okay, so yeah, 1 plus k squared is always going to be greater than or equal to 2k, and that's just going to be because k squared minus 2k plus 1 is equal to k minus 1 squared is greater than or equal to 0. And subbing nx for k, we get 1 plus n squared kx squared is greater than or equal to 2nx. So we can see that n square root x over 1 plus n squared x squared is going to be less than or equal to n square root x over 2nx equal to square root of 1 over 2 square root x. And notice that this is going to be Lebesgue integrable because it's Riemann integrable over this bounded interval. So it's Lebesgue integrable. All right, so now that all the conditions are met, we can apply the dominated convergence theorem. We have a dominating function, we have our sequence, so we have limit as n goes to infinity of f sub n, our f sub n is n squared of x over 1 plus n squared x squared is equal to the limit as n goes to infinity of s sub n. And notice that we showed the pointwise limit is 0, so we have this is equal just to 0 dm. It's equal to 0, and we're done.